The universe is filled with countless celestial bodies, each with its own unique characteristics and mysteries. Among these, some planets are known not for their beauty or potential for life, but for their sheer terror and harsh conditions. These planets, scattered across the cosmos, have environments so extreme that they challenge our understanding of what is possible. Join us on a journey to explore the most horrifying planets known to humanity as we delve into the science and unimaginable realities that make them the true nightmares of space. Imagine stepping onto HD 189733b, a distant exoplanet located 63 light-years away in the constellation of Vulpecula. This gas giant, slightly larger than Jupiter, presents a mind-boggling scenario. Here, it rains glass sideways. The vivid blue color of this alien world might evoke images of peaceful ocean waves, but make no mistake, this is a hellish landscape. The clouds on HD 189733b are laced with silicate particles, which, when condensed, form tiny shards of glass. Driven by ferocious winds howling at speeds reaching 5,400 miles per hour, these glass particles are whipped around the planet in a deadly high-speed sandblasting cycle. It's a stark reminder of how hostile environments beyond Earth can be. The winds on HD 189733b are among the fastest ever recorded, creating brutal conditions that are beyond inhospitable. These supersonic gusts propel the razor-sharp rain horizontally, transforming the weather system into something akin to a never-ending natural disaster. From a scientific perspective, this infernal climate provides invaluable insights into atmospheric dynamics under extreme conditions. The vivid azure hue, researched and confirmed using the Hubble Space Telescope, is primarily due to the silicate particles in the atmosphere that scatter blue light. This knowledge not only intrigues us, but also expands our understanding of the varied and often violent nature of exoplanetary weather systems, painting a dramatic picture of what lies far beyond our solar system. Corot 7b, an exoplanet located 489 light-years away in the constellation Monoceros. This rocky planet, similar in size to Earth with a diameter about 1.5 times greater, orbits perilously close to its star, resulting in extreme conditions that boggle the mind. Temperatures on the day side of Corot 7b soar to a scorching 4,700 degrees Fahrenheit, hot enough to not just melt rock, but vaporize it entirely. Imagine a world where molten rock evaporates, forming dense, scorching clouds that eventually condense and fall back to the surface as liquid lava rain. This molten downpour creates rivers of lava that wind their way across the landscape, an ongoing phenomenon far more terrifying than any natural disaster experienced on Earth. The night side of Corot 7b, though relatively cooler, plunges into freezing temperatures that contrast sharply with the day side's blistering heat. This massive thermal gradient yields violent weather patterns, including ferocious storms, as heat energy is transferred across the planet. The millennia-long erosion under such cataclysmic conditions renders the surface perpetually volatile and vividly hellish. For scientists, the study of Corot 7b offers a tantalizing glimpse into the extremes of planetary science. It serves as a striking reminder of the diversity and extremity of planets in our universe, highlighting just how unique our Earth's relatively stable climate truly is. K2-141b, an exoplanet located around 200 light-years from Earth in the constellation Aquarius. This distant world stretches the limits of our imagination with its extraordinarily harsh environment. On K2141b, blazing temperatures reach upwards of 5,400 degrees Fahrenheit on the day side, where an ocean of molten lava spans across its surface. This seething sea, composed of liquid rock, churns incessantly, driven by the planet's close proximity to its star. From above, a rock vapor atmosphere blankets the landscape, an atmosphere comprised of evaporated minerals like sodium, silicon monoxide, and silicon dioxide. The concept alone of such an atmosphere presents a truly alien, almost apocalyptic vision of what a planet can be. Shifting to the night side, however, the temperature plummets drastically to -328 degrees Fahrenheit, a stark contrast creating an incredible dynamic affecting the planet's atmosphere and surface. With such extreme differences, mineral vapors condense on the cooler side, leading to a continuous cycle where these solidified particles are transported back into the molten ocean via relentless supersonic winds that rage across the planet at speeds of over 3,000 miles per hour. For planetary scientists, K2141b offers an unparalleled natural laboratory to observe and understand geological and atmospheric processes under conditions far removed from anything on Earth. Peering into such extreme environments sharpens our perspective on what constitutes habitability and the myriad forms planetary systems can take across the cosmos. Envision standing on the surface of Gliese 436b, an exoplanet orbiting a red dwarf star 30 light-years away in the constellation Leo. This Neptune-sized world defies our earthly expectations by harboring a form of hot ice. Unlike the ice we know, which melts when heated, the ice on Gliese 436b remains solid despite scorching surface temperatures that exceed 800 degrees Fahrenheit. The key lies in the extreme gravitational forces exerted by the planet's own mass, which compress the water molecules so tightly that they form exotic states of ice, known as Ice 7. This ice remains solid even at temperatures that would boil water on Earth, giving rise to the mind-bending phenomenon of burning ice. As you imagine witnessing this spectacle, consider the shimmering alien landscape bathed in the glow of its dim red star. High pressures ensure that the water remains frozen, yet its high temperature suggests it's anything but cold. This means encountering a bizarre world where heat and ice coexist in defiance of our typical understanding. The discovery of such unique planetary conditions enriches our comprehension of the diverse forms that matter can take across the universe. Studying Gliese 436b enables scientists to better grasp the physics of extreme environments and the properties of materials under unprecedented conditions. Such worlds broaden our view of the cosmos, proving time and again that the universe holds marvels beyond our wildest imaginings. Imagine the uninhabitable furnace that is Kelt 9b, an exoplanet situated approximately 670 light-years away in the constellation Cygnus. This gas giant endures blistering temperatures that reach up to 7,800 degrees Fahrenheit, making it one of the hottest exoplanets ever discovered. To put that in perspective, this is hotter than many stars, including our own Sun's photosphere. Kelt 9b orbits extremely close to its parent star, Kelt 9, a blue A-type star. It completes a full orbit in just 1.5 Earth days, locked tidally so one side forever faces its searing star, experiencing relentless, intense radiation that strips molecules apart in its atmosphere. The energy is so extreme that even robust molecules like hydrogen are torn into atomic fragments. Visualize standing on Kelt 9b's dayside. The sky would appear incandescent, possibly a stark white due to the overwhelming radiation. Yet being a gas giant, there's no solid ground to stand on, only thick, churning layers of vaporized metals and other elements. The ultraviolet radiation from the star is intense enough to ionize heavy metals like iron and titanium, making the atmosphere a laboratory-like cauldron of high-energy particles. The incredible heat from Kelt 9b's star ensures that these metallic vapors remain in a gaseous state, never condensing into droplets or forming clouds as we know them. Studying such an extreme exoplanet provides astronomers with valuable insights into atmospheric chemistry and dynamics under conditions vastly different from anything in our solar system, broadening our understanding of how planetary atmospheres can evolve under the influence of intense stellar radiation. HD 100546b, a nascent gas giant orbiting a star 320 light-years away in the Musca constellation. This planet is still in the tumultuous throes of formation, surrounded by a chaotic disk of gas and dust. Unlike the more mature planets in our solar system, HD 100546b is swaddled in a dense, hazy envelope where gravitational forces are actively pulling in material, leading to intense and often violent accretion processes. Here, the planetary environment is incredibly dynamic, with temperature fluctuations and energetic outbursts as the planet interacts with this circumstellar disk. The surface, if it can be called that, is a swirling, opaque blend of gases and dust, hardly a stable or solid ground to venture upon. The young planet's intense youth means it is still radiating heat from its formation, contributing to extreme atmospheric temperatures that are hostile to any form of known life. Additionally, the gravitational interactions within the protoplanetary disk create instability. Powerful shock waves from high-velocity collisions of planetesimals and smaller debris generate enough energy to keep the atmosphere turbulent and erratic. For scientists, HD 100546b offers a priceless window into planetary formation processes that sculpt worlds from chaotic disks into the more organized systems we see around mature stars. Observing this environment helps astronomers understand not only how planets like HD 100546b come into being, but also glean insights into the early conditions of our solar system, thereby piecing together the evolutionary history of planets. HD 149026b, a unique exoplanet located about 257 light-years away in the constellation of Hercules. Often described as a super Neptune, this gas giant boasts an exceptionally dense core laden with heavy elements such as iron and silicates. This core is believed to be as much as 70 times the mass of Earth, a staggering concentration that would produce crushing gravity gradients and extreme pressures far exceeding those found on any planet within our solar system. Such an environment would be utterly unforgiving, where the notion of standing upright, let alone surviving, is rendered impossible due to the immense gravitational pull. This high-density core has immediate and profound effects on the planet's atmosphere and overall structure. The sheer mass of the core influences the surrounding gaseous layers, compressing them into a compact and turbulent atmosphere characterized by searing temperatures of over 2000 degrees Fahrenheit. Surrounding the dense core, the atmosphere roils with high-energy particles and complex chemical interactions driven by the heat and pressure. For scientists, HD 149026b presents a captivating anomaly, challenging existing models of planetary formation and composition. It underscores the diverse architectures that planets can assume and enriches our understanding of what constitutes a planet. Analyzing such worlds expands our horizon, showing us that even seemingly familiar planetary names like gas giant can encompass exotic and unexpected phenomena far beyond what our own solar system offers. Consider the extreme and utterly unforgiving environment of Kepler-13 an exoplanet located approximately 1,730 light-years away in the constellation Lyra. As one of the most massive hot Jupiters known, with a gravitational force 6 to 8 times stronger than that of Earth, stepping onto this planet would be an unthinkable challenge. The immense gravity would crush anything not built to withstand such pressures, making human survival impossible. Every movement would feel like an enormous effort, as if walking under the weight of an enormous invisible shroud. Kepler-13. Ab's atmosphere further compounds its inhospitable nature. Known for its burning temperatures, the planet boasts a relentless heat reaching up to 5,000 degrees Fahrenheit due to its close orbit around its parent star. This proximity results in a tidally locked rotation, meaning one side perpetually faces the star's intense radiation, while the other lies in perpetual darkness. The day side swathes in a ceaseless furnace where it is hot enough to vaporize metals, and the night side plunges into a frigid, starkly contrasting cold. The planet's peculiar atmospheric conditions include vertical winds that pull titanium oxide, an ingredient found in sunscreen, into the upper atmosphere on the day side, only for it to rain down again on the night side. This results in a stratospheric temperature inversion, an unusual atmospheric phenomenon seen in very few other worlds. Imagining life under such conditions stretches the limits of creativity and reveals the vast diversity of planets that populate our galaxy. For scientists, studying Kepler-13 provides compelling insights into atmospheric dynamics, gravitational influences, and the complex behaviors of matter under extreme conditions. As we unravel the mysteries of such distant and exotic worlds, it broadens our comprehension of planetary science, offering a humbling perspective on the uniqueness and relative serenity of our own celestial neighborhood. GJ-1214b, an intriguing exoplanet lying some 40 light-years away in the constellation Ophiuchus. Often referred to as a water world, this planet likely harbors an abundance of water, but not in forms we are accustomed to on Earth. The high-pressure environment compresses this water into exotic states, such as supercritical fluids, substances that exhibit properties of both liquids and gases. The steamy atmosphere is thick with vapor, generating an oppressive sauna-like condition across the entire planet. Temperatures remain consistently high, estimated around 400 to 500 degrees Fahrenheit, making traditional life support and cooling systems crucial for any potential survival scenario. In this dense, steam-filled atmosphere, the air is heavily laden with water vapor, creating visibility and breathing challenges. Specialized suits would need to be engineered to deal with high humidity and heat, effectively functioning as personal life support systems to extract and regulate breathable air while maintaining a survivable internal temperature. The suit would also have to withstand the immense pressure exerted by the thick atmosphere, akin to being thousands of meters underwater on Earth. Any structures or habitats would need to be built with materials capable of resisting the corrosive and high-pressure environment, possibly drawing on advanced materials sciences to ensure longevity and stability. For scientists, GJ-1214b offers a compelling look into the possibilities of ocean planets, and the behavior of water under extreme pressures and temperatures. Understanding these alien oceans and atmospheres expands our knowledge of planetary formation and the various environments in which water, the cornerstone of life as we know it, can exist. It also challenges researchers to reconsider where and how life might arise beyond our home planet, driving forward the quest to identify potentially habitable worlds among the stars. Titan, Saturn's largest moon, a world shrouded in a dense orange-hued atmosphere rich in nitrogen and laced with methane. Although not a planet, Titan is one of the most intriguing destinations in our solar system, featuring vast methane lakes and rivers, and cryovolcanoes that spew icy, ammonia-rich slush instead of molten rock. The temperatures on Titan are bone-chilling, plunging to around -290 degrees Fahrenheit. One of the primary challenges would be the sheer cold, requiring specialized thermal suits not only to maintain body warmth, but also to protect any equipment from the frigid conditions that could freeze and render them inoperable. Navigating Titan's surface presents a unique set of challenges. The thick atmosphere, about 1.5 times denser than Earth's, along with the lower gravitational pull, approximately 1/7 that of Earth, creates an eerie, otherworldly environment where parachuting or even using winged suits for exploration could be conceivable. However, the hydrocarbon lakes and seas pose their own risks, requiring airtight and corrosion-resistant materials for any exploratory vehicles to avoid the toxic effects of liquid methane and ethane. Furthermore, the cryovolcanoes, with their icy eruptions, can alter the landscape dramatically, necessitating constant vigilance for sudden geological changes. From a scientific standpoint, Titan offers a cornucopia of discoveries. The complex organic chemistry occurring in its atmosphere and on its surface, driven by solar radiation and cosmic particles, is of particular interest. Studying these processes could provide insights into prebiotic chemistry, potentially offering clues about the early Earth and the origins of life. Titan's methane cycle, analogous to Earth's water cycle, involves evaporation, condensation and rainfall, creating a dynamic and ever-changing environment. Exploring Titan pushes the boundaries of our technology and understanding, giving us priceless glimpses into the adaptability of life and processes in extreme environments. WASP 121b, a gas giant exoplanet located about 880 light-years away in the constellation Puppis. This close-orbiting hot Jupiter is subjected to such intense radiation from its parent star that the upper atmosphere reaches temperatures hot enough to break water molecules into their constituent hydrogen and oxygen atoms. This extreme UV radiation not only serves as a molecular disruptor, but also drives a vigorous atmospheric escape, with hydrogen and oxygen atoms being rapidly stripped away into space. The environment is lethal. Without adequate protection, exposure to this high-energy radiation would be instantly fatal to any known form of life. To survive on WASP 121b, one would need highly sophisticated shielding technology. Spacecraft or habitats would need to be enveloped in advanced materials, specifically designed to block or absorb ultraviolet and other forms of high-energy radiation. These materials might include specialized multi-layered composites that incorporate UV-resistant polymers and radiation-absorbing alloys, similar to spacecraft shielding, but on a significantly enhanced scale. Additionally, any mission to WASP 121b would require robust magnetic shielding to deflect the charged particles and plasma emitted by the nearby star, akin to Earth's own magnetosphere, but artificially created and much more potent. The atmosphere's chaotic nature, shaped profoundly by the radiation, poses another challenge. High-energy particles create a volatile and shifting atmospheric composition, rendering conventional chemical detection methods unreliable. Scientists would need to design advanced sensors capable of withstanding the extreme environmental conditions to study the atmospheric chemistry effectively. Instruments would likely incorporate redundant systems to account for rapid atom breakdown and unpredictable chemical interactions. Despite these formidable obstacles, studying WASP-121b holds invaluable scientific merits. Observing such processes in situ can deepen our understanding of atmospheric chemistry, particularly in exoplanetary contexts, and illuminate the broader dynamics of planet-star interactions. This exoplanet exemplifies the sheer variety and extremity of planetary environments, challenging our technological and scientific boundaries while broadening our perspective on the cosmos's possibilities. HD 37124c, an exoplanet orbiting its star approximately 109 light-years away in the constellation Taurus. This gas giant is known for its extreme weather conditions, which include ferocious storms and high-speed winds that make even the harshest weather on Earth seem benign. Wind speeds on HD 37124c can reach several thousand miles per hour, a velocity that would shred any conventional spacecraft or habitat to pieces in moments. These high-speed winds circumnavigate the planet, driven by intense temperature gradients and dynamic atmospheric processes that we are only beginning to understand. Surviving on HD 37124c would require engineering marvels that push the limits of current technology. Structures and vehicles would need to be designed with advanced materials capable of withstanding extreme mechanical stress, possibly utilizing composites that can endure both high pressure and temperature variations. Additionally, any attempt to explore or station devices in this hostile environment would necessitate autonomous, highly adaptive robotics equipped with fail-safes to operate amid rapidly changing conditions. These robots would require advanced AI to predict and react in real time to the planet's volatile weather patterns, avoiding the numerous dangers presented by sudden shifts in wind speed and direction. The extreme weather on HD 37124c also means that visibility would be significantly compromised. Thick, fast-moving clouds composed of exotic chemicals could obscure vision and sensors, making navigation hazardous. Furthermore, the atmosphere's chemical composition, potentially rich in toxic gases and lacking in oxygen, would necessitate completely sealed life support systems for any human explorers. These systems would need to filter and recycle air, while also mitigating the effects of corrosive atmospheric components, ensuring that the inhabitants are not exposed to harmful substances. LHS 1140b, a rocky exoplanet located about 40 light-years away in the constellation Cetus. This super-Earth orbits within the habitable zone of its red dwarf star, but it poses significant hurdles due to its high gravity and intense radiation. LHS 1140b's gravity is estimated to be around 3 times that of Earth's, making even the simplest movements feel like a monumental task. The muscular and skeletal strain would be immense, and without proper acclimatization and support systems, sustaining life as it is on Earth would be near impossible. To cope with the high gravity, explorers would need specialized exoskeleton suits designed to assist with movement and reduce the load on muscles and bones. These suits would need to be lightweight yet incredibly strong, incorporating advanced materials like graphene composites that provide strength without adding cumbersome weight. Furthermore, physical conditioning and training would be essential before even attempting to set foot on LHS 1140b, preparing the body to deal with the increased gravitational force. The intense radiation from the host red dwarf star presents another significant danger. Red dwarfs are known for their frequent and powerful stellar flares, which can bombard the planets in their vicinity with harmful ultraviolet and X-ray radiation. This radiation can strip away atmospheres and render the surface inhospitable. Any habitats or suits designed for LHS 1140b would require robust radiation shielding, possibly utilizing layered materials that can absorb and deflect high-energy particles. Additionally, underground habitats could offer a natural barrier against stellar radiation, providing a safer environment for long-term habitation. Imagine the profound challenges and potential dangers of navigating the skies of Kepler-7b, an exoplanet orbiting a sun-like star roughly 1,000 light-years away in the constellation Lyra. Kepler-7b is a gas giant slightly larger than Jupiter, but it boasts a climate that's far more peculiar and hazardous. High-altitude clouds composed of silicate particles loom in the upper atmosphere, creating a reflective layer and contributing to the planet's high albedo. These silicate clouds can generate intense heat and scatter incoming starlight, turning the atmospheric environment into a cauldron of searing temperatures and particulate matter. Even though it's a gas giant with no solid ground, traversing the silicate-laden atmosphere of Kepler-7b would be fraught with peril. These tiny glass-like particles, while suspended in the upper atmospheric layers, can be incredibly abrasive and destructive, akin to sandstorms on Earth, but on a much more intense and continuous scale. Any attempt to traverse this atmosphere would require highly durable materials that could withstand relentless erosion. Spacecraft or exploration probes would need advanced shielding technologies, using composites that can endure high temperatures and constant wear from the silicate particles. Additionally, the extreme heat in these high-altitude clouds poses further risks. Temperatures on Kepler-7b can reach over 1,700 degrees Fahrenheit, which would instantaneously compromise conventional materials used in spacecraft construction. Thermal protection systems would need to be engineered to withstand prolonged exposure to such heat while maintaining operational integrity. Cooling systems would be crucial to regulate internal temperatures and prevent overheating of critical components. Moreover, the intense radiation from Kepler-7b's parent star adds another layer of complexity. This radiation, coupled with the unpredictable nature of atmospheric dynamics, would make navigation and sustained communication challenging. Instruments and sensors on any exploratory mission would need to be radiation hardened and designed to function reliably within highly variable environmental conditions. Imagine an alien world where the weather is not just unpredictable but intensely ferocious, capable of whipping up winds and storms beyond human comprehension. Welcome to HAT P11b, an exoplanet located approximately 123 light-years away in the constellation Cygnus. Known for its temperamental weather, HAT P11b can experience wind speeds surpassing 1,000 miles per hour and violent electrical storms that make Earth's hurricanes seem like gentle breezes. Surviving such an environment would require masterful engineering and a keen understanding of atmospheric science. First, any habitable structure on HAT P11b would need to be built with materials far more resilient than those used on Earth. Think of hyper-durable alloys and composite materials that can withstand extreme shear forces and rapid temperature fluctuations. These structures could be anchored deep into the planet's crust, similar to how oil rigs are moored in the deep ocean to prevent them from toppling. Moreover, these habitations would likely be equipped with advanced weather prediction systems, using quantum computing to process and predict storm paths with near-perfect accuracy. By understanding the magnetic field interactions and solar influences that likely drive HAT-P11b's turbulent weather, inhabitants could seek sanctuary in reinforced underground bunkers periodically. Personal survival gear would include adaptive climate control suits, providing both insulation from extreme temperatures and protection against high-velocity particles driven by the brutal winds. In this bizarre and hostile atmosphere, human ingenuity would find new avenues to shine, perhaps revealing more about our own planet's potential for extreme weather as we unlock the secrets of surviving on HAT-P11b. Stepping onto the surface of 55 Cancri E, often referred to as the Diamond Planet, would be an experience beyond science fiction. Located about 40 light-years away in the constellation Cancer, this super-Earth is a celestial enigma. With surface temperatures soaring over 4,000 degrees Fahrenheit, you would feel the searing heat long before you ever set foot. The intense thermal radiation would be catastrophic for any known Earth-built materials or human protective gear. Simply put, the environment is far beyond anything survivable with current technology. If we suspend disbelief and imagine a scenario with futuristic, heat-resistant technology that allows you to withstand such extreme temperatures, you would then encounter a landscape unlike any other. The high-pressure carbon interior of 55 Cancri E, combined with scorching temperatures, could indeed lead to a geologic layer rich in diamond. You might find yourself walking over a surface that glitters and refracts light in a dazzling, almost surreal manner. The ground beneath your feet would be exceptionally hard, potentially jagged and rough from the crystalline structures, making each step both precarious and awe-inspiring. The intense atmospheric conditions, likely filled with silicate vapor clouds, create a heavy, almost oppressive feeling that presses down on you, coupled with a twilight due to the thick atmosphere absorbing and scattering light. Despite such an inhospitable environment, the mere thought of traversing a planet with vast diamond deposits adds a layer of exotic allure to 55 Cancri E, urging us to dream about what lies beyond our earthly confines and pushing the envelope of human exploration and ingenuity. Surviving on Kepler-70b, a blisteringly hot exoplanet with surface temperatures exceeding 10,000 degrees Fahrenheit, requires a suspension of known physical and biological limits. Imagine this. Temperatures on Kepler-70b can reach levels hotter than some stars, specifically cooler red dwarfs. Under such extreme conditions, survival would necessitate leveraging theoretical materials and technologies far beyond current human capabilities. First, the notion of even approaching Kepler-70b with conventional spacecraft would be unthinkable. The intense heat would vaporize any known metals and composites. Thus, to survive or even explore this hellish environment, your craft would need to be equipped with an extraordinary thermal shielding system. Think along the lines of a magnetic shield or a dynamic plasma field, capable of deflecting and dissipating heat far more effectively than any material barrier could. Once on or near the surface, you'd be reliant on a habitat constructed from hypothetical metamaterials designed to reflect and emit heat away faster than it is absorbed. a concept grounded more in advanced theoretical physics than in today's engineering. Additionally, you would likely be encased in an exosuit outfitted with a sophisticated cooling system, perhaps borrowing concepts from photonic crystals to refract heat, combined with advanced thermoelectric materials that convert thermal energy into electricity, thereby powering the suit itself. Inside the suit, a network of microfluidic channels continuously circulates a supercooled fluid to maintain a livable internal temperature, akin to how blood vessels help regulate human body temperature. Air and life support systems would need to be completely sealed, providing an autonomous mini ecosystem immune to external conditions. Even with these extreme measures, the relentless radiation and extreme temperatures of Kepler-70b represent an environment so hostile that current human survival there remains firmly in the realm of speculative science fiction. This leads us to ponder the boundaries of our technological ambitions and the ultimate resilience of human ingenuity. WASP-18b, a gas giant located approximately 325 light-years away in the constellation Phoenix. With an extraordinarily short orbital period of less than 1 day, WASP-18b completes a full orbit around its star in just about 23 hours. The result? Scorching temperatures that can reach upwards of 4,000 degrees Fahrenheit, hotter than molten lava and verging on the edges of stellar heat. In such conditions, survival by any conventional means is sheer folly. If one could hypothetically stand on a solid surface, assuming a gas giant could have such a feature, it would feel as if you were walking on the surface of the sun. The air, or more accurately, the gaseous envelope, would be an inferno of hydrogen and helium heated to incandescence. Any attempt to approach would necessitate a spacecraft with advanced heat-resistant technology, perhaps using an active cooling system employing ultra-efficient heat sinks and radiative barriers made from materials yet to be discovered. Furthermore, the planet's short orbital period means it experiences extreme tidal forces, causing significant gravitational stress that contributes to its violent weather patterns. Imagine colossal storms driven by rapid temperature gradients and turbulent wind speeds. Protective gear would therefore need to be a marvel of engineering, heat repellent, pressure resistant, and capable of withstanding dynamic atmospheric changes. Such suits might incorporate a flexible, self-healing thermal coating that repels heat and repairs damage in real time, coupled with an internal environment mimicking Earth's temperate conditions through a series of intricate life support systems. Even in this speculative scenario, the oppressive heat and tumultuous atmosphere of WASP-18b presents survival challenges that defy our current understanding of materials, science, physics, and engineering. Yet, pondering such a hostile world pushes the boundaries of human imagination and underlines the incredible variability of planets in our universe, each with its own set of extreme conditions waiting to be explored. Picture a landscape where every inch of ground is an unending expanse of molten rock, where the surface is bathed in a relentless sea of burning red and orange. Kepler-10b, an exoplanet about 564 light-years away in the constellation Draco, offers such a vision. Known as a lava planet, it possesses scorching surface temperatures that soar well above 2,000 degrees Fahrenheit, hot enough to melt most metals. This extreme heat is due to its remarkably close orbit to its host star, taking a mere 20 hours to complete a single revolution. Living on Kepler-10b would first and foremost demand unprecedented advances in thermal technology. Any habitation would necessitate the construction of structures with active cooling systems and heat shields, possibly inspired by the most advanced theories in thermodynamics and quantum mechanics. Such buildings would likely be underground to avoid the searing surface heat, with complex networks of tunnels and chambers akin to a vast subterranean city. The underground habitats would be maintained at a stable temperature through cutting-edge geothermal energy conversion systems, using the immense heat outside to power and cool the internal environment. Venturing outside would require personal suits mirroring the technology of habitats, equipped with ultra-high temperature resistance and thermal regulation systems. These suits would need to cool the wearer constantly, using advanced phase change materials that absorb and store heat energy while providing breathable filtered air. The visual panorama outside would be striking, a world glowing with the persistent light of molten rock, where rivers of lava carve new paths across the landscape and noxious gases release into the smoldering atmosphere. Walking on Kepler-10b would not only challenge your physical endurance but also your psychological resilience, as the very air would shimmer with the oppressive heat radiating from all around. Even with all this speculative technology, the experience of living on Kepler-10b is something that presently exists only in the realm of imagination and future science fiction. Nevertheless, considering such extreme environments expands our understanding of planetary science and the rigorous demands of survival on worlds so vastly different from our own. Venus, often dubbed Earth's evil twin, presents a daunting array of challenges for any potential exploration, let alone habitation. Imagine a world where the atmospheric pressure at the surface is over 90 times that of Earth, equivalent to the crushing depths of a terrestrial ocean nearly a mile beneath the surface. The suffocating atmosphere is primarily composed of carbon dioxide, with clouds of sulfuric acid perpetually drizzling corrosive rain. Surface temperatures soar above 870 degrees Fahrenheit, hot enough to melt lead. Survival on Venus would require audacious advancements in technology and an unwavering resolve against seemingly insurmountable odds. To withstand these extremes, any exploratory or habitable structure on Venus would need to be engineered to a level far beyond our current capabilities. Protective habitats would have to be constructed from superalloys and advanced ceramics resistant to both high temperatures and corrosive environments. These structures would be pressurized to create a livable internal atmosphere while combating the external crushing pressures. The habitat's exterior would need a dual-layered design, the outer layer to deflect the relentless sulfuric acid rain and insulate against intense heat, and the inner layer to maintain a stable, Earth-like environment for inhabitants. Personal exploration outside these habitats would be even more challenging. Advanced exosuits would be required, crafted from next-generation materials such as graphene-reinforced composites to resist crushing pressure and corrosion. These suits would integrate a network of micro-electromechanical systems, MEMS, to continuously regulate temperature and pressure, providing a breathable atmosphere with efficient life support systems. Movement in such a hostile environment would be cumbersome, with visibility hampered by the dense toxic air and a thick veil of acid clouds, leading to an eerie yellowish gloom that engulfs the landscape. Even with these theoretical capabilities, life on Venus as we consider it today is a testament to human ingenuity stretched to its limits. Scientific ventures such as floating cloud cities in the more temperate altitudes of Venus's atmosphere or robotic explorations are more feasible in the near term. Yet pondering the sheer extremes of Venus deepens our appreciation for the delicate balance that makes Earth so habitable and challenges us to think creatively about future space exploration and survival techniques. Kepler 452b, an Earth-like planet orbiting a star not too dissimilar from our Sun, yet significantly older and more luminous. Located approximately 1,400 light-years away in the constellation Cygnus, Kepler 452b is often hailed as a cousin of Earth. However, its advanced age means its star emits more intense solar radiation, bathing the planet in a relentless flood of high-energy photons. This extreme solar radiation poses a severe challenge to any potential settlers, demanding sophisticated solutions for protection and survival. First and foremost, habitation on Kepler 452b would necessitate constructing advanced shelters with unparalleled radiation shielding capabilities. These habitats would likely incorporate materials capable of absorbing or deflecting solar radiation, such as layered graphene composites or metallic foams infused with radiation-dampening compounds like boron carbide. Structures might be built partially underground to leverage the planet's natural geology for additional shielding, creating subterranean havens where settlers can escape the harsh surface radiation. Personal protection would also be crucial. Advanced suits designed for traversal outside these protective habitats would need to be equipped with multi-layered shielding. Think of biomimetic designs inspired by the radiation-resistant extremophiles found in Earth's harshest environments, combining materials that can self-repair and adapt to varying radiation levels. These suits would feature integrated dosimeters and active monitoring systems to alert wearers to rising radiation levels, automatically adjusting protective measures accordingly. Furthermore, they would incorporate advanced air filtration and cooling systems, safeguarding against intense UV radiation and maintaining a breathable, temperate microclimate. The environmental management would extend beyond immediate protection measures. Advanced terraforming and ecological engineering could introduce radiation-absorbing vegetation, bioengineered to thrive under high radiation conditions and provide natural barriers. Settlers might also rely on artificial magnetic fields generated by colossal electromagnets or plasma shields to mimic Earth's magnetosphere, providing an additional layer of protection from cosmic and solar radiation. Harnessing solar energy would be paramount, driving power systems using advanced photovoltaic cells designed to withstand and capitalize on the intense radiation. Inhabiting Kepler 452b requires a combination of forward-thinking innovations and an underlying tenacity to push the boundaries of current science and technology. While the extreme solar radiation presents a formidable obstacle, such challenges underscore the resilience of human ingenuity and our enduring quest to explore and adapt to the cosmos's farthest reaches. HD 219134b, a high-density rocky exoplanet located just over 20 light-years away in the constellation Cassiopeia. Known for its substantial mass, nearly 5 times that of Earth, this super-Earth is a place of extremes, boasting a gravitational pull that would make every movement feel laborious and taxing. The high density of HD 219134b hints at a composition rich in heavy elements like iron and silicates, contributing to an unforgiving, rugged terrain. Surviving on such a planet would demand not only physical adaptation, but also the utilization of advanced technologies to cope with its hostile environment. Habitations on HD 219134b would need to be robust, constructed from ultra-strong materials like carbon nanotubes and titanium alloys, capable of handling the increased gravitational stress. Structural engineering would involve reinforcing buildings to maintain integrity under intense pressure. Inside, life would have to be meticulously regulated, with artificial gravity environments adjusted to ease the strain on human bodies and sophisticated heating systems to combat potential temperature extremes. Exploring the jagged, rocky exterior of HD 219134b would demand spacesuits engineered to augment human strength and endurance. Imagine exoskeletons designed to counteract the crushing gravitational force, enhancing mobility and reducing fatigue. These exosuits would be equipped with adaptive support systems to assist with heavy lifting and stabilizing movements, integrated with advanced shock absorption technologies to navigate the planet's rugged landscape. Furthermore, these suits would need sophisticated life support systems to provide breathable air, regulate body temperatures, and protect against atmospheric anomalies, including high levels of radiation or toxic gases. Daily life on HD 219134b would undoubtedly be challenging. The high density could lead to a stark, metallic landscape with sparse vegetation, if any. Agriculture, if feasible, would rely on hydroponic systems sheltered within domes, protected from the harsh conditions outside. Water extraction and purification would be critical, requiring innovative techniques to harvest and sustain a supply from subterranean sources or atmospheric condensation processes. Life on HD 219134b would be a testament to human adaptability and technological prowess. The formidable environment would require continuous innovation and resilience, pushing the limits of what we understand about living in high gravity and potentially hostile conditions. It's a scenario that underscores our relentless pursuit to explore and make habitable the diverse worlds that populate our galaxy. Navigating the challenges of HD 219134b demands a breadth of innovative approaches to ensure human survival and adaptation. This super-Earth's gravity, nearly five-fold stronger than Earth's, would exert immense stress on the human body, making even simple movements seem Herculean. To cope with this, living and working on HD 219134b would necessitate advanced technology and strategies to mitigate the harsh surface conditions and gravitational intensity. Firstly, habitation structures on HD 219134b would need to be meticulously engineered to handle the planet's strenuous gravity. Constructed from resilient materials like carbon nanotubes and reinforced composites, these buildings would prioritize tensile strength and flexibility. Habitats might be embedded into the bedrock itself to provide additional stability and protection from seismic activity, which could result from the planet's gravitational forces. Inside, adjustable gravity environments could be created using centrifugal force in specially designed habitation modules, simulating Earth-like conditions to ease the daily lives of inhabitants and reduce physical strain. When exploring or working on the planet's surface, specialized suits would be indispensable. These exoskeleton suits would be designed to counteract the crushing gravitational force, incorporating advanced robotics and actuators to enhance physical strength and endurance. Augmented reality systems embedded in visors would provide real-time terrain analysis, highlighting safe pathways and the structural integrity of the ground, thus helping navigate the rocky, potentially hazardous terrain. These exosuits would also be equipped with comprehensive life support systems, managing temperature regulation, breathable air supply, and protection against potentially toxic gases or radiation found on the planet. Beyond personal gear, infrastructure solutions would be imperative. Terraforming initiatives could create microhabitats with controlled climates and gravity-neutral zones. Agricultural endeavors might rely on sophisticated hydroponic and aeroponic systems housed within these protected environments, ensuring food production and sustainability without exposure to the hostile surface. Adaptation to HD 219134B's conditions also hinges on psychosocial strategies. Regular physical training to increase muscle density and cardiovascular strength would be part of daily routines. Psychological support systems, including virtual reality environments replicating Earth-like settings, could help mitigate the mental strain induced by prolonged exposure to this alien world's extreme conditions. Coping with the immense pressures and rugged terrain of HD 219134B would not be simple, but with the integration of cutting-edge technology and adaptive human ingenuity, establishing a presence on this formidable exoplanet could one day move from the realm of theoretical challenges to a practical objective. It underscores the incredible resilience and inventiveness required to extend humanity's reach into the cosmos. Imagine trying to carve out a life on PSRB 1257 plus 12b, a planet that orbits a pulsar, a rapidly rotating neutron star, around 630 light-years away in the constellation Virgo. Let's just call it PSR Busy B, shall we? Living here would mean contending with incessant lethal radiation. Pulsars emit intense beams of electromagnetic radiation, including X-rays and gamma rays, capable of obliterating any unprotected organism or structure. Survival on such a planet would necessitate the most advanced and robust protective measures, pushing the boundaries of theoretical physics and engineering. To start, any habitation on PSR B 1257 plus 12b would need to be encased in layers of advanced radiation shielding. Imagine living in subterranean cities, burrowed deep within the planet's crust to utilize the natural rock as an initial barrier against radiation. These underground havens would be reinforced with ultra-dense materials like depleted uranium and lead, coupled with futuristic substances such as hydrogen-rich polymers and boron nitride nanotubes, which are exceptionally effective at absorbing different types of radiation. These layers would collectively provide a formidable shield, allowing life to flourish within safely insulated confines. Exploration and work outside these protective shelters might be akin to spacewalks in the most hazardous environments. Specialized suits would be critical, enveloping the wearer in a cocoon of radiation-absorbing layers. These suits would potentially include self-healing materials that can repair microdamage continually inflicted by high-energy particles. Integrated magnetic shield technology, drawing on principles similar to Earth's magnetosphere, could deflect incoming radiation, creating a protective bubble around individuals or mobile units. Advanced life support systems would maintain breathable air, comfortable temperatures, and protection from the pulsar's intense electromagnetic activity. Beyond physical protection, ensuring a sustainable way of living in direct bombardment by deadly radiation involves energy and resource strategies. The hostile environment would preclude the use of traditional solar panels, necessitating reliance on geothermal energy harnessed from the planet's interior or potentially nuclear fusion reactors that can operate safely within the highly shielded infrastructure, providing a steady and robust power supply. Psychologically, the constant threats would require robust mental health support systems. Virtual reality could simulate Earth-like environments, providing mental respite and a semblance of normalcy. Social structures and routines would be essential in maintaining morale, fostering a sense of community despite the overwhelming external dangers. Coping with life on PSR-B 1257 plus 12b requires a blend of technological marvels and human resilience. The unnerving reality of living under perpetual radiation bombardment is balanced by the potential to push the frontiers of human adaptability and innovation. While such a scenario currently resides in the realm of speculative science fiction, it continues to inspire the development of new technologies and strategies that one day might make surviving on such inhospitable worlds a reality. HD 209458b, also known as Osiris, a gas giant exoplanet located around 150 light-years away in the constellation Pegasus. This fascinating planet is subjected to such intense stellar radiation and wind from its parent star that it's literally losing its atmosphere, which streams away into space like a comet's tail. The challenges of surviving on Osiris would be unlike any other, necessitating innovative solutions to counteract the extreme conditions and atmospheric loss. Firstly, understanding that Osiris has no solid surface and is primarily composed of hydrogen and helium means that any habitable structure would need to float or hover in the upper layers of its atmosphere. These sky cities would likely resemble enormous airships, held aloft by the buoyant gases harvested directly from the planet's atmosphere itself. Constructed from advanced lightweight materials, perhaps graphene composites and aerogels, these floating habitats would be robust enough to withstand the high-speed winds and turbulent weather patterns typical of hot Jupiters. The relentless stripping of the atmosphere means that these habitable structures would also need advanced radiation shielding to protect against intense stellar radiation. Multi-layered protective shells incorporating materials like boron nitride and polyethylene would absorb and deflect harmful particles. Moreover, a dynamic magnetic shield could be employed around the habitat to mimic Earth's magnetosphere, deflecting charged particles and creating a more hospitable environment within. Energy production would rely heavily on advanced solar collection systems, capturing the immense amount of stellar energy available due to the planet's close proximity to its star. This energy could be stored in cutting-edge batteries and utilized to power life support systems, climate control, and radiation shielding. Ensuring a sustainable food and water supply would involve closed-loop ecological systems, incorporating hydroponics and possibly even vat-grown foods to make the best use of limited resources in a contained environment. Life aboard these floating habitats would be governed by routines and protocols to ensure safety and psychological well-being amidst such an alien environment. The constant awareness of the atmospheric loss and external dangers necessitates a carefully managed community, with mental health services, virtual reality environments for personal recreation, and robust social interaction to maintain morale. Surviving on Osiris involves not just overcoming the physical extremes, but also leveraging human ingenuity and technological innovation to create a sustainable microhabitat in an extraordinarily dynamic and hostile environment. While this scenario pushes the limits of current technology and engineering, it sparks the imagination and speaks to our potential to adapt and thrive even in the most challenging conditions the universe can offer. Lich, also known as PSR-B 1257 plus 12d, a planet orbiting a pulsar, would be akin to living in one of the most extreme environments envisioned. Pulsars are rotating neutron stars that emit beams of electromagnetic radiation, including deadly X-rays and gamma rays, which sweep across space like lighthouse beams. These powerful emissions create an irradiated environment that, without significant protection, would prove lethal for any form of life as we know it. First and foremost, survival on Lich would necessitate robust and comprehensive radiation shielding. Habitats would need to be embedded beneath the planet's surface to maximize natural protection against the pulsar's constant bombardment. Creating subterranean cities carved into the planet's crust would involve using materials like lead, tungsten, and futuristic radiation-absorbing polymers to construct multi-layered shielding. These habitats would be equipped with sophisticated filtration systems to remove any radioactive particles, maintaining a safe and clean living environment. Moving outside the protective habitats would require highly advanced exosuits designed for extreme radiation protection. These suits would include a combination of dense, radiation-absorbing materials and active magnetic shielding technology, somewhat akin to miniaturized versions of the Earth's magnetosphere. Such suits might also leverage self-healing fabrics that can repair microscopic radiant damage in real time. Given the varying radiation levels, incorporated real-time dosimeters would monitor exposure, dynamically adjusting the protective measures to remain effective. Energy resources would also need to be carefully managed. Conventional solar power would be non-viable due to the high radiation and pulsar's inconsistent light, so advanced nuclear power sources, possibly small modular reactors, SMRs, would be critical to provide a reliable energy supply. These power systems would be shielded with layers of protective materials and situated in isolated sections of the habitat to prevent contamination. Agriculture and water systems would similarly need meticulous design. Growing food and purifying water in such a hostile environment would rely on closed-loop ecological systems. Hydroponic gardens within radiation-shielded domes could provide food, and water recycling systems would ensure sustainability by constantly purifying and reusing the available supply. Mentally coping with life under such extreme conditions involves constant psychological and social support. Given the oppressive environment, virtual reality systems could provide simulated Earth-like settings to escape the rigors of the reality outside. Artificial intelligence could manage community schedules and ensure that inhabitants get sufficient mental and physical care, maintaining high morale and community spirit. Surviving on Lich, orbiting a pulsar, is a scenario that extends far into the realm of speculative science fiction. However, the theoretical solutions required highlight the incredible advances in technology, engineering, and human resilience needed to make such survival conceivable. It paints a picture of an indomitable human spirit, willing to push the boundaries of what's possible to explore and inhabit even the most challenging corners of the universe. Proxima Centauri b, an exoplanet orbiting our nearest stellar neighbor Proxima Centauri, presents unique and formidable challenges primarily due to extreme radiation from its host star. Proxima Centauri is a red dwarf, known for its frequent and intense stellar flares that emit powerful bursts of X-rays and ultraviolet radiation. These flares can dramatically increase the radiation levels on Proxima Centauri b, making the surface environment potentially hazardous for human life. To survive on Proxima Centauri b, one would need to construct habitats that offer comprehensive protection against the harmful radiation. These habitats would likely be built underground or within naturally shielded areas such as lava tubes or rock formations to capitalize on natural protection. This approach reduces the impact of surface radiation. The outer shell of the habitat would be composed of advanced materials such as hydrogen-rich polymers and boron nitride, which are highly effective at absorbing and deflecting radiation. This multi-layered shielding would ensure that the interior remains a safe sanctuary from the hostile environment outside. For those rare excursions outside the protective confines, advanced wearable technology would be essential. Radiation suits would need to be crafted from cutting-edge, densely layered materials that can block different types of radiation, including X-rays and ultraviolet light. These suits might also incorporate active cooling systems and provide breathing apparatuses to handle potential atmospheric hazards. Energy generation would also present a unique challenge. Traditional solar panels might be compromised by the frequent stellar flares and excessive radiation. Instead, energy solutions could include advanced nuclear fusion reactors or geothermal power, tapping into the planet's internal heat if such a resource is available. These power systems would necessitate robust shielding to protect against any radiation leaks and ensure a stable energy supply. Agricultural practices would require innovative solutions as well. Hydroponic and aeroponic systems housed within radiation-shielded greenhouses could produce food, ensuring a sustainable supply independent of the external conditions. Water purification and recycling systems would need to be extremely efficient and fully contained to prevent contamination. Social and psychological well-being would also be a priority. The harsh, isolated environment necessitates strong communal bonds and mental health support systems. Routine virtual reality simulations of Earth-like environments could provide much-needed mental respite and a sense of normalcy. Educational, recreational, and social activities facilitated by artificial intelligence could ensure a balanced lifestyle, mitigating the psychological stress of living in such an extreme setting. Living on Kepler 438b, a planet located about 470 light-years away in the Lyra constellation, presents a tantalizingly close analogue to Earth in terms of size and temperature. However, its host star, a red dwarf, poses a significant threat through frequent and intense solar flares. These flares emit bursts of high-energy radiation, including harmful ultraviolet, UV, and X-rays, which can be deadly without adequate protection and could disrupt any biological activity on the planet's surface. To survive on Kepler 438b, robust shielding against these frequent solar flares would be indispensable. Inhabitants would need to live in habitats constructed with advanced materials specifically designed to absorb and block high-energy radiation. These structures might be built underground or within natural formations, utilizing the planet's geology to provide additional layers of protection. The buildings themselves would be composed of thick layers of radiation-resistant composites, such as multi-layered graphene and hydrogen-rich polymers, effectively creating insulated fortresses that safeguard against the intense bursts of stellar radiation. For any outdoor activities or planetary exploration, specialized suits akin to spacewalk suits would be necessary. These suits would integrate multiple layers of shielding, advanced radiation dampening technologies, and sensor arrays to detect incoming solar flares in real time. The reflective outer layer would deflect UV radiation, while internal gel-like composite layers would absorb X-rays. These suits would include life support systems to maintain breathable air and comfortable temperatures, making sure that inhabitants remain safe and functional even during the most intense solar events. Energy generation on Kepler 438b would need to be resilient to the frequent flare activity. While traditional photovoltaic systems might be compromised by the radiation, leveraging geothermal energy or using nuclear fusion reactors could provide the necessary power without exposing critical infrastructure to direct solar radiation. These power sources would be housed in well-shielded facilities to prevent radiation damage and ensure continuous operation. Agriculture would need innovative indoor farming methods, protected from the harmful radiation by thick shielding. Advanced hydroponic systems within controlled, radiation-proof environments could provide a steady supply of food. AI-driven monitoring systems would maintain optimal growing conditions and ensure the health of crops, even in the event of prolonged solar activity. Psychological well-being would also be a key consideration, with frequent solar flares dictating life indoors for extended periods. Virtual reality environments could simulate Earth-like conditions, providing mental and emotional relief. Community and recreational activities would be enhanced by artificial intelligence to foster social bonds and support mental health, ensuring that the psychological impacts of a confined and highly controlled living experience are mitigated. Surviving the intense solar flares on Kepler 438b requires a seamless blend of advanced materials, science, innovative engineering, and sophisticated life support systems. While the environment poses significant challenges, the potential for human ingenuity to adapt and thrive even in such extreme conditions speaks volumes about our capacity to explore and inhabit the diverse worlds in our galaxy. This endeavor illustrates the resilience and fortitude needed for future interstellar colonization. Ogle 2005 BLG 390 LB, an exoplanet located approximately 21,000 light-years away near the center of the Milky Way, presents a challenge like no other. With surface temperatures plunging to around -364 degrees Fahrenheit, -220 degrees Celsius, this icy world requires exceptional technological solutions to survive and function. Known as a super-Earth, this planet's frigid conditions make it an immensely hostile environment for human life, demanding innovative approaches to habitat construction, energy production, and daily living. Habitations on Ogle 2005 BLG 390 LB would need to be brilliantly insulated to conserve heat and provide a safe, warm environment amidst the freezing wilderness. These structures would likely be designed as low-profile, dome-shaped buildings, minimizing exposure to the harsh external conditions. Constructed with advanced materials such as aerogel insulation and multi-layered graphene composites, these habitats would be able to retain heat efficiently. The outer shells would include thermal barriers capable of reflecting the intense cold away and trapping warmth inside. These habitats might be buried partially underground or encased in artificial permafrost layers, leveraging the planet's natural insulation properties to enhance energy efficiency. For energy production, relying on traditional solar panels would be impractical due to the planet's distant orbit from its host star. Instead, advanced geothermal energy systems might tap into potential subsurface heat sources, although these might be limited. More likely, nuclear fusion reactors would provide a reliable and robust energy source. Nestled within radiation-shielded facilities, these reactors could generate the necessary heat and power to maintain livable conditions within the habitats and support various life support systems. Surviving outdoors would necessitate ultra-insulated suits equipped with the latest in thermal regulation technology. These suits would be embedded with multiple layers of insulating materials, perhaps including aerogels and synthetic spider silk, known for their exceptional thermal resistance. Integrated heaters powered by compact fusion cells would provide warmth, ensuring that even the most extreme external temperatures are bearable. Additionally, the suits would incorporate sophisticated life support systems to supply breathable air, manage humidity, and monitor vital signs continually. Farming and food production would take place within highly controlled indoor environments. Hydroponic and aeroponic systems housed within heated and insulated greenhouses would allow for the cultivation of crops year-round. Artificial lighting, perhaps from LED arrays designed to mimic the sun's spectrum, would enable photosynthesis and healthy plant growth. These greenhouses would be integrated with closed-loop water recycling and nutrient management systems to maximize efficiency and self-sufficiency. Maintaining mental health in such an isolated and extreme environment would also be critical. Virtual reality could offer immersive experiences that replicate Earth-like settings, providing a psychological escape from the monotony and harshness of daily life on Ogle 2005 BLG 390 LB. Social activities, facilitated by communication technologies, would encourage community bonding and support networks. Enduring the extreme cold of Ogle 2005 BLG 390 LB requires a confluence of cutting-edge technology, innovative engineering, and psychological resilience. The challenges are immense, from maintaining warmth and energy efficiency to ensuring food production and mental well-being. Nevertheless, human ingenuity and determination could make survival on this icy super-Earth feasible, showcasing our incredible capacity to adapt and thrive even in the most inhospitable environments known to us. Adapting to the bone-chilling cold of Uranus requires a leap in human ingenuity and technology. Uranus is about 1,700,000,000 miles from the Sun, receiving only a fraction of the solar energy that warms Earth. The average temperature on Uranus is a frigid -371 degrees Fahrenheit. Protecting human life in these conditions would necessitate advanced thermal insulation and heating systems for any habitats. A combination of vacuum-insulated panels, advanced heating elements perhaps utilizing nuclear energy, and thermal suits capable of maintaining body heat would be critical. Engineers might also develop ways to harness and convert the limited sunlight and internal heat from the planet itself, if feasible. Compounding the challenge, Uranus doesn't rotate like Earth. It has an axial tilt of 98 degrees, essentially rolling around the Sun on its side. This peculiar tilt leads to extreme seasonal variations, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Adapting to these conditions means creating living environments that can manage prolonged periods of both extreme cold and moderate sunlight. For the long, dark winters, habitats could rely on artificial lighting powered by advanced solar panels or nuclear reactors to simulate day and night cycles, ensuring psychological well-being and circadian rhythm synchronization. During the extended periods of sunlight, cooling systems would need to ensure that habitats do not overheat. Advanced climate control technologies, potentially augmented by artificial intelligence to manage these environmental shifts, would be indispensable. Life on Uranus would thus be an extraordinary testament to human resilience and technological prowess in the face of extreme extraterrestrial challenges. Kepler-16b presents a remarkable scenario. Orbiting two stars, it experiences what is known as a circumbinary orbit. This dual star system is about 200 light-years away from Earth, occupying the constellation Cygnus. The presence of two suns means that the environment on Kepler-16b would be subject to complex and unusual light patterns and temperature fluctuations. Unlike Earth, where we have a relatively stable day-night cycle, Kepler-16b's days and nights would be unpredictable, with varying intensities of light and shadow as its two stars, one slightly smaller than the other, dance around each other and the planet. This situation complicates establishing a stable, predictable environment necessary for human habitation. One of the initial challenges would be managing the thermal variations resulting from red and orange dual suns rising and setting at different times. The temperatures on the planet have been estimated to range between -150 degrees Fahrenheit and -170 degrees Fahrenheit, making it an extremely cold world. Habitats on Kepler-16b would require advanced thermal regulation systems to handle these drastic changes. The intermittent and multiple light sources would also affect energy planning. Solar power systems would need to be incredibly efficient and adaptive, capable of harnessing energy from irregular and fluctuating sunlight. Adapting to life on Gliese 581c, a potentially tidally locked exoplanet located approximately 20 light-years away in the constellation Libra, would involve overcoming extraordinary temperature differences. This planet is thought to be tidally locked, meaning one side perpetually faces its parent star, while the other remains in eternal darkness. Consequently, the star-facing side would be subjected to scorching temperatures, while the dark side would experience frigid, icy conditions. Survival on Gliese 581c would likely hinge on establishing habitats in the narrow twilight zone, or terminator line, the transitional area between the hot and cold hemispheres where temperatures might be more moderate and capable of supporting life. Creating stable living conditions in the terminator zone would require advanced engineering. Habitats would need to be meticulously designed to regulate the influx of heat from the star-facing side and mitigate the cold from the dark side. Adaptive insulation systems, capable of dynamically responding to environmental changes, would be crucial. These systems could use phase change materials to absorb and release heat as needed, ensuring a stable internal temperature. Power generation in this unique environment might leverage both solar and geothermal energy, with solar panels capturing energy from the well-lit side and geothermal systems tapping into the planet's internal heat from the constant tidal forces exerted by its star. Human adaptation would also have to account for psychological factors, given the perpetual twilight environment. Artificial lighting would need to simulate a 24-hour cycle to support human circadian rhythms and overall well-being. Residents might also rely on virtual environments to experience a semblance of natural Earth-like settings. The adaptation process would extend beyond physical and technological means to include substantial mental health support systems. Inhabiting Gliese 581c would demand a harmonization of cutting-edge technology and human ingenuity to transform this alien world into a livable frontier. Imagine a planet where the weather swings so dramatically that you could experience a temperature increase of over 1,000 degrees Fahrenheit within a few short hours. This is the reality on HD 80606b, an exoplanet approximately 190 light-years away in the constellation Ursa Major. What sets HD 80606b apart is its highly eccentric orbit, resembling a stretched-out ellipse that brings the planet extremely close to its star at one point and then swings it far away at the other. This results in staggering temperature changes as the planet can heat up from around 500 degrees Fahrenheit to an astonishing 2200 degrees Fahrenheit during its closest approach to the star, known as periastron. Adapting to such extreme temperature fluctuations would be immensely challenging. Habitats on HD 80606b would need to be designed with robust thermal regulation systems capable of handling rapid and massive changes in temperature. Advanced insulative materials and automated climate control technologies would be crucial, designed to respond almost instantaneously to the rising or falling temperatures. These technologies might include heat radiators that can rapidly dissipate excess heat and thermal shelters with reflective coatings to deflect the intense stellar radiation. Moreover, cooling systems could incorporate advanced phase change materials that absorb heat during the planet's heated periods and release it during cooler times. Another layer of complexity is presented by the short duration in which these temperature changes occur. Human physiology is not adapted to endure such rapid environmental fluctuations, necessitating controlled environments that can stabilize internal conditions quickly. Psychological adaptation would also be critical, as such an unpredictable and harsh climate could impose significant mental stress. Training would be imperative to prepare inhabitants for the extreme conditions and rapid transitions. Thus, enduring the drastic temperature changes on HD 80606b would require implementing highly adaptive and resilient engineering solutions, while considering the profound physiological and psychological implications of living in such a volatile environment. Kepler-36b, located about 1,200 light-years away from Earth in the constellation Cygnus, shares an extraordinarily close orbit with its neighbor Kepler-36c. The proximity of these celestial siblings, sometimes just 1.5 million miles apart, is closer than any planetary bodies we've observed in our solar system. This intimate dance results in dramatic gravitational interactions, causing what's known as tidal forces, which would create significant stress on the planet itself and any potential inhabitants. The gravitational pull from Kepler-36c would likely induce severe geological activity on Kepler-36b, resulting in frequent and intense seismic and volcanic activity. Any human habitation would need to be engineered to withstand constant shaking and possible lava flows. Advanced materials capable of absorbing and distributing stress would be employed in construction, and real-time structural health monitoring systems would be essential to ensure the stability and safety of living quarters. These systems could include flexibly designed supports and foundations that can sway and adapt to the ongoing tremors. Moreover, the atmospheric conditions on Kepler-36b would be influenced by these gravitational interactions, likely leading to extreme weather patterns. The constant gravitational tug-of-war could produce violent storms, requiring robust and adaptable atmospheric management systems. Habitats would need features like retractable storm shields and advanced weather prediction technologies to offer timely alerts and responses. Gliese 876d, an exoplanet nestled about 15 light-years away in the constellation Aquarius, presents a formidable challenge for human habitation due to extreme tidal forces and potential volcanic activity. This exoplanet orbits very close to its star, completing a full orbit in just 1.94 Earth days, subjecting it to intense gravitational interactions. These interactions generate powerful tidal forces that could significantly deform the planet, stretching and compressing it constantly. This tidal flexing is similar to what we observe on Jupiter's moon Io, more about that later, known for its relentless volcanic activity due to similar forces. To endure these conditions, any human habitat on Gliese 876d would need to be constructed using cutting-edge adaptive architecture. Buildings would need to be designed with flexible structures that can absorb and dissipate the energy from constant seismic activity. Advanced materials, possibly incorporating smart alloys that can change shape in response to stress, would be essential. Additionally, subterranean habitats might be considered to mitigate the immediate impact of surface-level volcanic eruptions and seismic tremors. These underground facilities would require significant support systems to manage heat and air quality, given the potential for volcanic gases and ash. The extreme tidal forces would likely result in continuous and unpredictable volcanic eruptions, creating a hazardous environment. Sophisticated early warning systems coupled with real-time data analytics would be vital to predict volcanic activity and provide timely evacuation protocols. Thermal shielding and protective gear designed to withstand high temperatures and acidic gases would be necessary for anyone venturing outside. Moreover, maintaining psychological well-being in such an environment would be a challenge. Ensuring that habitats are equipped with amenities to provide comfort and normalcy would be critical. Such measures could include artificial recreation of Earth-like environments to help inhabitants cope with the stark and hostile conditions outside. Living on Gliese 876d would be a remarkable feat of human engineering and resilience, pushing the boundaries of what technology and resourcefulness can achieve in one of the most extreme environments imaginable.